us. He will speak about spinorial representations of orthogonal groups. Yeah.
Organizers for giving me this opportunity to present my work in the symposium. So I'll be talking about spinorial representations of orthogonal groups. This is a recent work with Rohit Joshi. Okay, so to set the stage, I will just define the terms that I would use. So let G be a Lie group, real Lie group, and pi be a real representation of G. So throughout this talk, I will restrict my talk with real representations only. And such a representation is called orthogonal if the image lies inside the orthogonal group. And the pin group is a non-trivial topological double cover of the orthogonal group uh, with a covering map rho, which is a map from pin V to OV with kernel plus minus 1. Here is the definition of the spinorial representations. So you start with a orthogonal representation of the Lie group G, so that the representation lands inside the orthogonal group OV, and you have this pin group, which is a double cover, and so the representation pi is called spinorial if there exists a homomorphism pi hat such that this diagram commutes. Okay. So in fact, all the representations of the orthogonal group are orthogonal, and we determine the spinorial representations of the orthogonal group. Rather, we give some criteria to determine the spinorial representation. So here I will briefly discuss about the pin group. So you take the real vector space V with the standard basis E1, E2 up to En, and associate the negative definite quadratic form with V. So one can define the Clifford algebra CV, which is the quotient of the tensor algebra by this ideal generated by the elements of the form V tensor V plus mod V square for elements in V. Without going into much details, uh, one can define pin group in this simple way. Uh, so the pin group is a subgroup of the group of units of the Clifford algebra, which is generated by the unit vectors in the vector space V, which also lies inside the Clifford algebra CV. Okay. So I will just mention the properties that the pin group has and we need for the calculations. So the basis elements EI, they also lie inside the pin group, and the image of these elements EI under the map rho are the reflection matrices. So the matrix REI is the diagonal matrix with -1 at the ith position, and everything else is 1. All the other positions are occupied by 1. Okay. And because of this negative definite quadratic form, we have the relations EI square is -1 and EI EJ is equal to minus EJ EI whenever I is not equal to J. Okay. So to get a flavor of the spinoriality business, let us do this simple example. So take the cyclic group of order 2, which is generated by this element G. And this we know that the irreps of C2 are just trivial and sign. So any representation pi of C2 will look like this. I have trivial representation appearing m0 times and sign representation appearing m1 times. And note that this is for the representations of C2 are all orthogonal. So pi in general is orthogonal. And the image of this element G under the representation will be this diagonal matrix uh, where -1 appears m1 times and the rest of the diagonal positions are occupied by 1. So let me denote this matrix by dm1. So we claim that the representation pi is spinorial if and only if m1 is 0 or 3 mod 4. So the proof is quite easy. Just note that this matrix DM1 can be written as product of reflections RE1, RE2 dot dot EM1, and from the using the relations in the previous slide, we get that REI is basically the image of EI under rho. So EI, these elements are elements lie in the pin group, and you take the image of these elements under this covering map, you get the reflections. So in fact, DM1, this matrix is the image of this element E1, E2 dot dot EM1 under the covering map. So one can take this element as a lift of G, the generator of C2, uh, in the pin group. So now the representation pi is spinorial if and only if there exists a homomorphism from C2 to the pin group, and that demands that the the order of this element should be 2. And using the relations EI square is -1 and EIJ is minus EJEI, one gets like this square is equal to -1 to the power this triangular number, and this triangular number m1 into m1 plus 1 by 2 is even if and only if m1 is 0 or 3 mod 4. So we have this. Okay. Okay, now let's take up the case of orthogonal groups. So we have the orthogonal group OM is equal to SOM direct product C2 when M is odd, and it is SOM, the special orthogonal group, semi-direct C2 when M is even. So we just call them the odd and even orthogonal groups for convenience. And for the sake of computation, I take the generator of the cyclic group C2 to be G naught, and the G naught is different for depending on the parity of M. So when M is odd, we take this minus I to n plus 1, which is where I to n plus 1 is the identity matrix of order 2n plus 1. And when M is even, we just take this particular matrix. This is like you take the identity matrix of order 2n minus 2 and just add a reflection block at the end. Okay. So I will just talk about the spinoriality of the even orthogonal groups, because similar results follow for odd orthogonal groups. So a representation phi of O to N is spinorial if and only if its restriction to the subgroups SO2N and C2 are spinorial. So we have in general proved a result like if G is a group which is a semi-direct product of G1 and G2 where G1 is connected, then the representation of G, a representation pi of G is spinorial if there are restrictions to the subgroups are spinorial. Anyway, so this is the case for the orthogonal group. Okay, now let us survey briefly the how the irreps of O to N comes. So you just start with an irreducible representation pi lambda of SO2N. So the representations are basically parameterized by the highest weights lambda, and take the induced representation to the orthogonal group, call it rho lambda, and there are two possibilities. So in the first case, rho lambda is irreducible. Uh, so in that case, if we take the restriction of rho lambda to SO2N, it decomposes as pi lambda direct sum pi g naught dot lambda, where pi g naught dot lambda evaluated at an element x is equal to pi lambda evaluated at g naught x g naught inverse. Note that we just need to determine the spinoriality of the representation rho lambda restricted to SO2N and C2. So therefore this is important. So when rho lambda is irreducible, we call these type 1 representations. And the other case is when rho lambda is reducible, In this case, it decomposes as the irreps pi lambda plus and pi lambda minus, where the dimensions of both the representations are same as dimension of pi lambda, uh, and these restrict to pi lambda plus minus restricted to SO2n is basically pi lambda, that is representation we started with. Okay, so in this case, we call these representations pi lambda plus minus as type 2 representations. And this is a fact that any irreducible representation of O2n is either of type 1 or type 2. Okay, so I will just mention the lifting criterion for representations of type 1 because a similar result is true for representation of type 2. Okay, so let this bracket denote the killing form for the Lie algebra of SO2n, and delta denote the half sum of positive roots for the Lie algebra of SO2n. Then we have this result. Uh, so the irreducible representation rho lambda of O2n for n greater than equals to 3 is spinorial if and only if both the following conditions hold. Okay, so we stated the result that rho lambda is spinorial if and only if its restriction to the subgroups SO2n and C2 are both spinorial. So these two conditions come from that result. So when you restrict rho lambda to SO2n, that representation is spinorial if and only if this condition holds. So this is like 2n n minus 1 by n into 2n minus 1 dimension of the representation of SO2n, and this quantity alpha lambda plus alpha g naught lambda, where alpha lambda is the inner product of these two elements. So this is even. So this is basically a result in the paper by Steven Spallon and Rohit Joshi, where they have like deduced all they have talked about spinorial representations of connected reductive groups in general, and in our paper this is just an addition, so this is disconnected. So for that we just need to think about what is the criterion for the representation pi lambda restricted to C2 is spinorial, and that happens to be this. The dimension of the representation of SO2n should be 0 or 3 mod 4. Okay. Okay. Now I will quickly talk about the Stiefel-Whitney classes of the representations of the Lie groups. So you just take a real representation pi of the orthogonal group, and one can associate something called Stiefel-Whitney class Wi pi, which belongs to the ith cohomology group of the orthogonal group with z mod 2z coefficients. Okay, and if I is greater than strictly greater than the degree of the representation, this quantity is 0 Wi pi. Okay, so the 0th Stiefel-Whitney class is 1, which is basically the unit element in the cohomology ring, direct sum of Hij, and we have this quantity called total Stiefel-Whitney class, which is the sum of the Stiefel-Whitney classes Wi pi, I varying from 0 to d. Okay, and one gets that the first Stiefel-Whitney class gives the determinant of the representation. Now the reason I am bringing this concept is there is a beautiful relation between spinoriality of a representation of a real Lie group, of course orthogonal representation, and the first and second Stiefel-Whitney classes of the representation. So it is given by this result. So I have just mentioned it for ON. It is generally true for any orthogonal representation of a Lie group. So a representation pi of ON is spinorial if and only if W2 of pi plus W1 of pi cup W1 of pi is 0. And using the concept of Stiefel-Whitney classes, we give a criterion for the spinoriality of the representations of the orthogonal group in terms of character values. So we denote by GI the diagonal matrix consisting of -1 and 1, where -1 is appearing I times. And without going into the proof, I will just state the result. Uh, so a representation pi of ON is spinorial if and only if both the following conditions hold. So it is like the dimension of the representation minus the character value at the element D1, that should be equal to 0 or 6 mod 8, and the dimension of the representation minus the character value at D2, that should be equal to 0 or 6 mod 8. Okay, so here is one more result. So let G be a reductive real Lie group and G naught has finite index in G, where G naught denotes the connected component containing identity, and let K denote the maximal complex, a maximal complex subgroup of G. Then an orthogonal representation phi of G is spinorial if and only if its restriction to the maximal complex subgroup is spinorial. Okay, so we can use this result to talk about the spinorial representations of GL and R, because uh, the orthogonal group is the maximal complex subgroup in GL and R, and we have the criterion for spinorial representations of, to detect the spinorial representations of ONR in terms of character values. So actually, this result follows. You take an orthogonal representation pi of GL and R. This is spinorial if and only both the following conditions hold. The conditions just depend on the dimension and the character value at this diagonal matrices T1 and T2. Okay, so here are some references. So this is the paper which goes with the same name, spinorial representation of orthogonal groups. We have done the cases for, like, we have considered little general cases here in the paper. It is, the preprint is available in the archive, and this is the paper by Steven Spellon and Rohit Joshi. They talked about, where they talk about the spinoriality of reductive groups connected. And okay, sorry. This paper is important because this gives some wild character formula for disconnected Lie groups. Of course, when the connected component is simple, he just considers that. But we have used this the results from this paper extensively, and this is the paper where this is the paper where this concept of Stiefel-Whitney classes of real representations of finite groups are there. There we can generalize them to compact Lie groups also. And this is a paper by Dipendra Prasad and Dinakar Ramakrishnan, who first considered the lifting of orthogonal representations on a very different context. So, okay, thank you.
Thank you so much. We thank the speaker for the excellent talk. There are a few questions for the speaker.
Oh, maybe I will just.
The chat section.
Okay, sorry, I have to.
First question is that I can see from Jyotirmoy Singh, says that, do you use Hadamard matrices? Do you consider projective representations? So Shayan made some comments.
Okay, maybe I will. You just tell me the questions, because I will share.
The question is, do you use Hadamard matrices? And the second is, do you consider projective representations?
No, we haven't used the Hadamard matrices, and we really haven't used projective representations. This, so one can. So you can read the paper by Steven Spellon and Rohit Joshi. There they have like detection methods. So you take a connected reductive Lie group, and you just restrict the representation to the diagonal torus, and this spinoriality is detected from the restriction to the torus, and from there they have deduced things. Now in our paper we have just used the fact that I mentioned here, the spinoriality of C2, which is, I will just go back to the slide. Yeah. So it just depends on the, so you take this matrix and it just depends on the multiplicity of the eigenvalue of -1. So somehow playing with it. We haven't really used projective representations.
Okay. There is another question from Sagar. Maybe you can see. It says that are there any literature available of spinoriality in case of UN or SPN?
Yeah. So as I said, the case UN is there in the paper by Rohit Joshi and Steven Spellon. They have like studied it for connected reductive groups. So also I think there is a paper, there is a thesis in the thesis of PhD thesis of Rohit Joshi. He has done extensive calculations for various classical groups, and the thesis is available in Steven Spellon's homepage. You can go and have a look at it. And I can see one more question. I believe spinorial lifting can be studied.
So this was more or less answered, I guess, but you can continue.
Using the second cohomology of the group with, yeah, that I have just mentioned, right?
Yeah. I mean, I asked is before you mentioned this Stiefel-Whitney class.
Yeah.
Okay.
Actually, for this paper and in my PhD thesis, I have just studied the spinorial representations of the symmetry groups, the finite group, symmetry group. So there I have extensively used this second cohomology of the groups and the criteria that W2 of pi plus W1 pi cup W1 of pi 0 if and only pi spin.
Yeah. Right. Thanks.
Okay. Are there further questions for the speaker? If not, let's thank the speaker once again.